In this example, we're going to take a look at kind of mixing everything together. Since we've seen 3 problems already with shells. So we're going to see examples of using shells going back to disks, but also see an example of using shells to be able to find the volume rotated about a vertical axis that's not going to be the y-axis. So in this example, we have 2 functions, root x, cube root x, and we want to find volumes revolved about 3 different axes. Okay, so the first one's the y-axis. The y-axis we know is a shell method. The second one we have y equals 4. Now y equals 4 is a horizontal, so that's one where we're going to use the disk method. X equals 4 is a vertical axis, so that's going to be the shell method. All right, so depending upon how long this runs, we might just do 1 or 2 of these, and then in another video do the other one. One thing we should probably do is we need to try to graph this, find the points of intersection, and then figure out which is going to be the top function and which is going to be the bottom function. All right, so let's do that first. All right, so I'm going to go to our friend Wolfram Alpha. And let's graph y equals square root of x. And y equals x to the 1/3 power. Okay, don't forget you're going to put in parentheses. All right, so let's see what happens. All right, so here are our functions. We should probably use it in quadrant 1. Okay, so I'm just, because we know the square root of x only exists in quadrant 1. So let's say from like 0 to 4. Still does this sort of thing. So not sure if I made a typo or something like this. So let's say and y equals. So let's see if that works a little bit better. There we go. Okay. So it looks like that right here at 1 is going to be our point of intersection, which we'll verify. But it looks like that the top function is going to be the cubic. The lower function is going to be the square root function. And you can see by the color coding here. Okay. So if we go back here and graph this, all right, so on the same axis, right? So we have something like this, and then we have something like this. All right, so it's going to be a pretty small area or volume whenever we compute it. And then the lower one is going to be y equals square root x, and the top one is y is equal to the cube root of x. Okay, so we could use our graphing calculators, we can use fooplot, we can use Wolfram Alpha, we can use a table of values, lots of different ways that we could graph this. All right. So let's revolve it about the y-axis to start, right? And I think it's pretty clear to everybody that the height is actually going to be the distance that's found from subtracting square root of x from cube root of x, okay? So like the height of each of our shells is going to be cube root of x minus square root of x, okay? The distance from the x-axis is still going to be x no matter what, okay, as x changes. The only other thing we need is the point of intersection for this, okay? So for our points of intersection, that's going to be when square root of x is equal to cube root of x, all right? Or x to the 1/2 is equal to x to the 1/3, all right? Now to solve this, what I'm going to do is I'm going to raise both sides to the 6th power. All right. And the reason I do that is because I know 6 times 1/2 is 3, 6 times 1/3 is 2. So at least it'll get rid of those fractional exponents. All right. So this will be x cubed equals x squared. We could subtract x squared or x cubed from both sides. Doesn't matter. Factor out an x squared. And clearly we get x equals 0, which we knew. And this one gives us x which equals 1, which we already knew too from the Wolfram Alpha. Okay, so now remember, for the volume, that's going to be equal to 2 pi by using our shell method, in this case 0 to 1 or a to b, of x f of x dx. But in this case, our function is going to be the height, which we remember we said was cube root of x minus square root of x. Okay, so we can set this up nicely, and our volume is going to be 2 pi integral 0 to 1 x cube root of x. I'm going to write as x to the 1/3. Square root of x is going to be x to the 1/2, right? And that's going to be our dx. Okay. If we distribute the x through, which we need to be able to have a shot at evaluating this, this is going to be equal to 2 pi integral 0 to 1. We just add 1 to each of the exponents. So that's going to be x to the 4/3 minus x to the 3/2 dx, right? And so now we can go ahead and integrate term by term. This is going to be 2 pi quantity x to the 7/3 divided by 7/3 minus x to the 5/2 divided by 5/2, ranging from 0 to 1. And finally, what we can do is we can just go ahead and multiply by the reciprocal, substitute 1, substitute 0. So we get 2 pi 3/7 1 to the 7/3. That should be a 7/3, sorry, minus 2/5 times 1 to the 5/2. And we know if we substitute 0 back in, we're just going to get 0. Okay, so realistically, what we have here is 2 pi 3/7 minus 2/5, right? And then if we get a common denominator of 35, that's going to be, so we're going to multiply by 5 is 15 35ths. Should be a 35 there. And then fortunately, 14, okay, so this is 15 35ths. And then we're going to multiply by 7, so that's going to be 14 35ths. And so ultimately, we just end up with 2 pi over 35. Right? So if you have two functions that are binding the area, then instead of just using the one function, you just take the difference of the top minus the bottom, just like we did with the area problems before. Right? So in the next video, what I'm going to do is I'm going to go ahead and use the disk and washer method. And then also I'll use the shell method to show you what happens if we revolve around an axis other than the y-axis.